This program prints the prime number between number 3 and number 1000. I saw this interesting video that compared the performance of the Commodore 64 versus the Amstrad CPC using this program, and at the end the result is that the Commodore is slow. So I decided to use the assembly to improve the performance of the Commodore. This video is just a comparison of Commodore BASIC versus assembly, and this is not a comparison of the 6502 versus Z80. Before to begin, I compared the performance of the VIC20 with the Commodore 64 for this program, and the VIC20 resulted 20 seconds faster. So for the moment I will start using the assembly with the VIC20. Then I will show a further improvement for this program using the capability of the Commodore 64. The two important operations in assembly for this algorithm are the square root and the division. For the square root, I found the code in 6502.org. Source code repository, integer math, root calculator, and here is the source code that is perfect for our scope, because calculate the 8-bit root of a 16-bit unsigned integer. While for the division I copied this source code. This is the page. Also in this case this code perfectly fits our scope, because it's a 16-bit division. What really counts here for us is the address of the remainder, not the result of the division. In fact, if the remainder is 0, we don't have a prime number, while if the remainder is always different from 0, we have a prime number. After I found the required code, I used CBM Program Studio to create the assembly subroutine. This assembly code practically is a subroutine that executes the tasks similar to the original BASIC program from line 15 to line 60. Here is the assembly code. The important addresses here are the address of the remainder, that is 5904 in decimal, and clearly the starting address of the subroutine, that is 5600 in decimal. Here is all the assembly. And here is all the machine code generated by CBM Program Studio. Once we have the machine code, we can load it on the VIC20. This is the machine code. Now the subroutine is loaded and we need the basic program to run it. Here is the basic program. From line 10 to 20, the program reset to 0 the variables used by the subroutine and set the value of I to 1. Then at line 30 starts the main loop cycle. Line 40 calls the assembly subroutine at address 5600 in decimal. Then at line 50, if the remainder is different from 0, we have a prime number and the value of the prime number is printed. Otherwise, it is not a prime number and nothing is printed. As we can see, this is quite faster compared to the basic version. Clearly, this is an improvement. but we can improve more if we remove completely the BASIC and we go for 100% assembly. And now I show the speed for the program written 100% in assembly. This is the machine code. Now that the machine code has been loaded on the VIC, we can run it. Also in this case, the improvements is visible. Now it takes less than 7 seconds. A smaller improvement can be achieved removing the scrolling, but the improvement is less than a second. As we have seen now, the speed is improved a lot, and it's difficult to check and read all the values while they are computed and displayed on the screen. So now I'll use the Commodore 64 to display all the prime numbers, till up 1000, all together in the monitor. As you can see, all the values are displayed on the screen with a good speed. Now the question is it possible to go faster than this using the Commodore 64? And the answer is yes. There are two ways. The first way is to optimize the code, while the second is to look for a faster algorithm. Because at the moment I have no idea how to optimize the code, it will be more interesting to proceed for the second way. A faster algorithm that can be used for this limited range of values is the sieve over Eratosthenes. This program is divided in three parts. The first part is the creation of the array, with the sides that represent the highest value of the interval. The second is the application of the sieve to determine the prime numbers, and the third part print on the screen the prime numbers. This program takes around 24 seconds, 22 if I remove the messages, so it's about 6 times faster than the previous. Okay, now it will be very interesting to check the performance of this algorithm using the assembly. Here it is all the code in assembly for the sieve over Eratosthenes for the Commodore 64. And here it is, the machine code. Now we load the machine code inside the Commodore 64. The machine code has been loaded and we can run the program. Excellent! Now it's very fast. So thanks to Eratosthenes and the assembly, I can't say that the Commodore is slow.